Hi, welcome everyone. Today's last session, how to write a heap profiler. I'm Million. I really like tooling. I happen to have written quite a few tools in my time already. And today I want to kind of demystify how to build one of such tools, what happens behind the scenes, and how you can maybe leverage that yourself to build a special-made, purpose, hand-built tool for your needs. So I kind of hope that you have had enough C++ for today because, well, today this last talk won't be too much about C++ as it turns out. Rather, when we look at what is required, many of the things that I'll show you are not standardized at all as part of the C++ standard. They are standardized by platform-dependent manuals. So it happens to be that most of these tools are very, very platform-specific. So in this case, I like Linux. So all of the stuff that I'm going to show you is only valid on Linux in the way that I implemented it. The core concepts, though, they apply equally to all the other platforms. You just have to find a corresponding equivalent library or whatever to do these kind of things. This talk contains information that I learned the hard way. So originally, 10 years ago or so, I always thought that writing a profiler is only for like black magic people, and that's not the case at all. It's actually very, very trivial once you learn how to put the little puzzle pieces together, right? So this talk hopefully shows you what are these puzzle pieces and how can you put them together yourself. Lots of dirty details here, so language lawyers beware. All of the source code that I'm going to show is part of this GitHub repo, so you can just go there after the talk and check it out yourself, compile it, play around with it, change it. It's open source. Go ahead. Right, so where did I learn all of this? There are two tools that I've written recently-ish. So in May 2013, I started HeapTrack, a heap memory profiler for Linux, which is like the core foundation of this talk. Anyone in the audience who's used HeapTrack? Not too many. Those who haven't used it, but target Linux, try it out. It's open source. And then more recently, in December 2016, I started Hotspot. So anyone heard of that one? A UI for Linux Perf? Also not too many. So if you happen to have used Linux Perf and found it kind of awkward to use on the command line, try out the UI. There's an app image. Just download it, make it executable, run it, drop in a replacement for Perf report. I kind of like it, and I got good feedback. So this is where I learned all of this. And you can also look at these implementations for further inspiration in case you wonder how this could all be leveraged. So this talk is essentially showing you how to do heap profiling based on tracing and not sampling, right? And tracing is actually quite a useful debugging and profiling technique. It's been being used all over the place, right? Perftrace, strace, ltrace, well, HeapTrack, obviously. But I guess I'm not the only one who isn't ashamed to say I'm still using printf, tracing, debugging, profiling, whatever, just add a short clock statement to my code to check how long does it actually take on the wall clock, right? So it's being used all over the place. The thing, though, is once you start writing one of these tools yourself to deploy it on a larger scale, to actually make it possible to run your trace on real-world applications, it starts to become quite hard. Like if you would do printf tracing for malloc already, you would completely obliterate the performance of your application because these like memory allocations, they happen thousands, millions of times per second, right? So you have to be very performance conscious when you write one of these things. And then there are some other features that I demand from a good tracer. Most notably, when I don't use the tracer, I don't want to pay any price for not using it, right? So there are some approaches to tracing which require you to recompile your code, and then this adds tracing capabilities. I bet it exists for heap profiling too. I don't do this. Instead, this talk will show you techniques to, well, not change your code at all, but instead you could say we kind of hack into an application to get notified whenever an allocation happens. And I will show you how this is done. And additionally, one cool thing that is kind of hard to do is supporting runtime attaching. So imagine you have a long-running server application, not on Google or Facebook scale, but let's say a single machine somewhere, and after a week, a day, a month, whatever, you realize, damn, memory allocations pile up. I seem to have a leak or something that looks like a leak. What do you do now, right? You can't just restart your application, wait again for a month, and then get some results back, right? You want to runtime attach and see instantly what's going on there. And doing that is kind of tricky. But thankfully, there's Stack Overflow with people that helped me out, and now I'm helping you out and tell you how to do this. And right, one of the key takeaways maybe from this talk is when you think about writing your own tracer, don't start from scratch. Build on top of existing proven solutions. So there's definitely a support in Perf for like user space probes or static dtrace-like probe points. There's LTTNG. A more recent addition to this tooling landscape is LLVM's X-Ray. And there are many, many more tools like that. And they solve many of the hard problems for you. They are oftentimes reusable, so better not start from scratch. Use those, and then build on top. Great. So what do we actually want to achieve when we say we want a heap profile? There are basically 4 steps, let's say, at least on this slide. The first one is going to be we want to inject custom code. It's like, yeah, let's be hacker man. Let's run stuff that isn't compiled into an executable, but like I have compiled it completely separately. How can I get it into my other library code, executable, you name it, and execute it? And not only that, the second step then is I want to be notified whenever the other application calls specific trace points. So in this case, it's library functions that we are going to trace. malloc and free, you name it. We'll see that in a bit. And then just being notified that a memory allocation happened is by far not enough. And this is actually a crucial point. You need a backtrace to make use of these kind of tracing data, right? Because otherwise you will see, I happen to have called malloc a lot. Thank you. But the actual interesting part is where did I call it, right? Without the call stack, without the backtrace, the tracing data is, in my opinion, pretty much useless. So this is a very, very hard problem when you would have to start from scratch. When you know the right libraries to use, this is actually doable. Because remember, memory allocations happen like thousands, millions of times per second. If you look at bad code, that is. So the last part then is we want to make tracing, profiling as quick as possible. And a very, very common approach there is to delay the post-processing step, such that while recording, you don't actually pay the price of symbolization, resolving of inline frames, yada, yada. I'll show you how this is done later. So it's, on one hand, a profiling aspect, or no, a performance aspect. And on the other hand, it is also a functionality aspect, because when you think about embedded systems and you want to profile heap allocations on an embedded system, you won't be able to symbolize backtraces because you usually don't have the debug symbols available on an embedded device, right? So there's an inherent distinction between recording data, getting backtraces, and then later on analyzing those with debug symbols and so forth. So this is an important distinction. So this is the content of this talk. Now, when I'm talking about memory allocations, I'm usually going to say heap memory. I think the proper C++ term is dynamic storage. Anyways, the important part is I'll just concentrate on libc functions. Because on Linux, at least, it happens to be the case that even operator new and all the overloads, they just end up calling libc functions, right? So when we want to profile or get notified about operator new int 100, we don't need to do anything special, which is good because these operators may be typed or whatever. Let's just ignore them and just live in a C world for now. A more problematic observation is that people, when they care about performance, tend to write custom pool allocators. And when they bypass malloc and free, there's basically no easy way to get notified about that because they then end up calling syscalls. And most of the techniques that I'm going to show you now are not applicable to syscall tracing. You would have to call something like ptrace or perftrace or so to get notified about an mmap call. If that is not the case and anyone knows how to do that, please tell me. I would be very interested in learning how to do that without ptrace. Good, so we'll ignore the last part for today. Which brings us to, preloading. This is the first step that we are going to talk about. I guess most of you know what I will show you, or maybe you have at least heard of this trick called LD preload. And that one is pretty nice. I mean, you just take some library. You need to specify it by its full path. That's one limitation. And you set that absolute path to this LD preload environment variable. And whenever you then run any application, the linker on Linux, so LD Linux, will see this environment variable and see like, oh, cool, you want to preload this library? Yeah, sure, let me do that. And now it's as if some app was linked dynamically against this library that you provided. Cool, right? That's actually pretty trivial. And there are some other nice side effects here because the dynamic linker is also the one that will resolve library calls, right? And well, in C++, we have this term, this whole ODR concept, right? But this is outside of C++. This is like on the linker level of Linux in this case. And that one doesn't care about ODR at all. It just looks at, oh, you want to call malloc? Sure, let me look through the list of shared libraries, and I'll pick the first match. And LD preload happens to win over all of the other dynamically linked libraries. So that makes it actually pretty damn easy to intercept malloc and friends. We just have to provide functions that have the same name. Cool, let's see how this goes. So we built a library with essentially, in this case, a single symbol that is exported. So I use extern-c here. This malloc will have exactly the same mangled symbol like the function that I want to trace. And now when I LD preload that library, my malloc will be called instead of the real libc malloc. So that's good already. I get notified about the malloc. But, well, you asked for memory, right? So I still have to provide memory. Otherwise, you would just crash. So what do I do now, right? This is another interesting aspect here. I could end up building my own malloc implementation, but that's obviously a bad idea. So instead, what I end up doing is I leverage, again, nice API that is available from the linker. I call dlsym, which is part of libdl, and you need the dlfcn.h header for that part. And dlsym, when you call it with a string, asks essentially the linker, give me back a symbol with this name. And when you pass this rtld next flag, it will skip the current shared object, which is important because otherwise you would find yourself again, right? You don't want that. You want to find the next library that happens to implement this. So pretty cool. And what I get back here, I originally had auto here, but that kind of hit an interesting side effect here. What you get back is a void star. So a void star, but what I want is a function pointer to malloc, right? Anyone in the audience knows what C++ standard says about function pointers and void star pointers. Are they compatible? I think what they say it's platform defined or undefined or whatever. Well, on POSIX at least, it has to be compatible because DLSIM exists, and DLSIM returns a void star. And if it wouldn't be compatible, you wouldn't be able to do anything with DLSIM. So that's cool. So on Linux at least, I definitely can reinterpret cast this void star pointer to whatever is malloc. So I just use decal type of the malloc function pointer, and note how I do. So this actually finds myself in this case, right? But I could wrap this in a template or whatever, make it reusable, and then the : malloc would find the global malloc, which is good. So now I get the original function back, and now it's pretty trivial. The kind of hooking you do then is you just call the original function, which gives you a pointer back, and then you can trace it. At this stage, we are just going to print data. So we just print it to standard out, and we print the size and the return pointer value, and then return the original allocated pointer. Cool. And that works quite nicely. So we can just quickly check the test application with NM, which gives us some insights into the symbols of this application. And we see it does reference malloc, but it's undefined at this stage, right? This is my application that I want to trace. If I look at libc, it has a symbol. Uppercase T means it's actually defined within this shared object. And the same happens for my preload shared library that I want to put into LD preload. So now I can write a little script that essentially puts my library into LD preload. That is the interesting part really here. Absolute path, that's important. And then it passes whatever other arguments you pass to that script. So now what I can do, I have this one malloc example, which really just does malloc and free. And I compile it without compiler optimizations, because otherwise the compiler would go in and say, that's crappy code, I can just remove the buffer altogether, you don't do anything with it. So the one malloc.cpp I compile without compiler optimizations, and then I run it through this little preload shell script, and I see 2 mallocs. The first one is pretty large too. Well, what we see here is actually part of printf, because our tracer calls printf. And we were lucky here, because I mean, usually what you have to do in one of these memory allocators is to make really sure that you either don't call malloc again within your tracer, or you kind of guard against recursion, because this could easily blow up. Printf, thankfully, only allocates once a big buffer, and then it's done. So this happens to work. Cool, lucky. Good. So we got our code inside. We injected using LD preload. And thanks to the dynamic linker, we also intercepted malloc. That was pretty good. We got far. Great. And before I want to advance, I want to show you another little trick when you write these kind of inceptors, which helps you in debugging, is this LD debug equals bindings environment variable, because that tells the dynamic linker to spit out some more information to you while it resolves functions or symbols. And what we see here is it first binds libc.so, and it finds a normal symbol malloc in there, that's good. And then it binds libgcc.so, again, libc malloc, and then libstd, C++, and so forth. In this case here, I didn't preload anything, right? So it's always going to call libc.so's malloc version. So this is kind of nice to see what's going on behind the scenes. And now I'm actually preloading, and it looks different, because now we actually see that in most of these cases, it's now going to use our libpreload.so, But at the very end, within our preload, or lib preload.so, it will actually find malloc within libc, and that's the DL-sim, essentially. And then we get the normal output. Cool, that's good. Great for debugging. So now we already solved 2 parts of the problem, right? You could say, oh man, we are nearly done, 50% done. Well, it turns out the really hard part is just about to start. Stack unwinding. Has anyone ever done custom stack unwinding within C or C++ or Fortran application or whatever? I see 2 hands go up. 3, great. So usually not something that you would do, right? I mean, obviously you can throw an exception in it, behind the scenes it will unwind, but when you actually want to get the backtrace, that's completely different, right? You need some kind of support to actually do that. And when you look at how to do that, oh boy, does it get complicated quickly. There are different approaches. The best one, if at all possible, is relying on frame pointers. This is fast, this is well established, it's very easy to understand what's going on. But on pretty much all Linux distributions by default, and well, within GCC and Clang by default, everything is compiled with -f omit -frame -pointer. So if you want to use frame pointers, you have to pass -f no omit frame pointer. And if you want to allocate malloc, for example, you have to make sure that your real malloc actually is compiled with frame pointers, because otherwise, or basically anything inside your backtrace needs to be compiled with frame pointers, because otherwise, as soon as you hit any frame without a frame pointer, your backtrace will break and it starts to become very confusing to analyze the results. So it turns out frame pointers is basically unusable. If you look at the documentation of libc's backtrace function, which, well, as the name says, gives you a backtrace, it kind of says it relies on a frame pointer. So libc's backtrace is not usable, or you have to recompile your whole system. So Gentoo people or Yocto-based distros, you could probably pull this off, but that's not us. So instead, what we need to do is we need to unwind just like an exception would unwind. And that's doable. There are these .eh frame sections for x86 or the ARM EX IDX section for ARM. And there, one further alternative would be relying on the debug frame section inside the Dwarf debug information. That's all cool, that's possible, but it turns out to be really, really hard to do that. Because essentially you have, I believe, more or less Turing-complete state machine within these kind of exception debug information or within these unwind tables. So interpreting that just to get a backtrace happens to be quite complex. And that's also why exceptions being thrown is, well, zero cost when you don't throw them. But as soon as you throw exceptions a lot, it starts to be very, 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 very slow. So don't do that in a hot loop. So we'll have to figure out how to do that. Some alternatives would be Intel Last Branch Record or ShadowStack. I'm not going into detail there. If you want to look at that, Google it up or drop by the ShadowStack page. It's kind of interesting. So it's an active field of study on what to do here. Right, so libc's backtrace depends on frame pointers, so it's unusable. There's elf-utils as a cool library. We'll use that in a bit too. But it's super complex to use that for unwinding. I believe you could somehow manage to make it work, but the API that there is right now is mostly meant for unwinding from within a different application. So this use case where you get a stack copy and then want to unwind that stack copy on a completely different machine. So for that case, it would be kind of cool to use that. But if you just want to get a backtrace within your application, libunwind, and with libunwind I mean this specific libunwind, because there are quite a few libraries that have the same name, not the libunwind in GCC, not the libunwind in Clang, no, this libunwind. That one is super easy to use. It's extremely fast because it does tons of caching behind the scenes. and it's also very, very feature rich. So it supports all kinds of things like compressed debug sections, split debug sections, whatnot, ARM, MIPS, you name it. And using that is actually trivial. Like instead of backtrace, you just call unwind backtrace. Oh yeah, and by the way, do define this, whoop, I don't want to show that one yet. Define this unwind local only before including lib unwind, then it becomes magically faster. And then you can just call unwind backtrace, fill that into some buffer, and leverage that. So that's trivial. And the cool thing about that is this unwind backtrace is super fast, right? One of the key blocking steps for me to write something like HeapTrake a couple of years ago was not knowing how to do unwinding a lot. And with lib unwind, this is doable. Like it's trivial even. And that's what I mean with demystifying how these kind of tools work, right? When you know the right building blocks, it starts to become trivial to build them. Cool. So that's a very important step. We can plug that into our preload mechanism, right? And now, whenever I run this on application, I get a backtrace. What's the problem here? A couple people laugh. I think you get the point, right? Like it's this, can you give me a pointer? And someone replies with, yeah, obviously I can. OX dead beef, so funny. You can't make any sense out of it, right? The core problem now becomes actually symbolizing these pointers, because otherwise, once again, you got to stop a step further, but hit yet another wall, right? Because no one can make use of this as is. Cool. Which brings us to yet another section on symbol resolution. I'll give a rough introduction and then go into details there because it happens to be, quite a hairy situation. The digger we deep, the more complicated it kind of becomes. But at the end, I hope to show you some usable results there. Cool. Let's start. The goal really is, once again, to take a pointer value and translate it to a human readable symbol. And because this is CPPCon, I couldn't get away with this chance and not using it. A human readable symbol, right? That is a single symbol. That's not 10 of them, that is one symbol. Could anyone guess what this is? Because when you would write it, it's actually kind of tiny. I guess it's std_map something, right? Well, if you would apply some kind of heuristics to it and replace the type defs in there, you end up with this. It's a std_map of a string to a vector of a map of int to strings. What happened here, right? I mean, well, type defs happened, right? And at the level of the linker, the type defs don't exist anymore, and you only see whatever got resolved to the end. So keep this in mind, because once we want to do demangling, we won't want to do something like that ourselves, right? Once again, we need to look for a solution that does this kind of stuff for us, because parsing that would otherwise be a nightmare. Cool. So yet again, if you would want to go from the huge symbol to the tiny symbol, this actually requires heuristics, because the type def will change based on your STL implementation, maybe even on the version of the STL. So we won't talk about how to do that today. Hotspot has one way to do that based on some heuristics for, I believe, GCCs, lib, std, C++. But you could apply the same tricks to other libraries. Okay. Now, a core concept that you need to grasp is that on Linux, by default, you get address-based randomization, right? And you get, when you compile a shared object, it is compiled in a position-independent way. That means symbols aren't represented by their absolute address at which they will show up in your application, but rather they somehow are built in a way that they like you encode an offset to wherever the shared library gets mapped into your address space, basically. So we need to do the reverse, because when we want to find out a symbol, we need to know this offset to our shared library. So what we do essentially is we look into the mappings of our application. For now, I will use the proc meta file system, or whatever you call that. It's easy to get the point across, but in a bit I'll show you a different way to do that. So within that file system, you find this maps file, and there you can see all of the shared libraries and where they get mapped to, and maybe even other files that are not executable and whatnot. And now you essentially need to do a lookup into this table to find the map. And you need to take the first address. So essentially here, it's this first address at the left, top left of this block. This is what you need to use as your base address. You subtract that from your input instruction pointer address to get an offset. So this OXD9F, that is our offset. This now we can actually use to get the symbol back. Great. Because with this value, we can actually ask Adder2Line or a similar tool to symbolize us or give us information back about the symbol. So what we start off with is Adder2Line-P to make it human readable in some sense, and then -E, the path to the library or executable, and then -A and the offset into this library for which you want to see some tangible symbol results back. And this is what you get by default, which is, as the name says, the address and the line, so line and file number, which is good, but it's not really what we need, or not enough. We also need functions, so, well, yeah, let's pass -F. And -F gives us, in this case, a mangled name for whatever, right? It's, yet again, not very readable, so we have to pass -C to actually make it demangle the symbol. And now the symbol becomes so large that it doesn't fit the slide anymore, so I cut it down. It's a different symbol than the one before. It's not as bad, but it's already, I think, spanning 3 lines or so. So this is good, but turns out it's still not enough. We are writing C++, we're using abstractions all over the place, right? And one of the core principles to make these abstractions cheap to a certain degree is inlining. And if you symbolize a backtrace without taking inline frames into account, you will have a very, 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 very hard time in figuring out what the hell is going on. Because it will start look like in main you are calling some internal libc++ function, and you're like scratching your head and wondering, where the hell did I write this? I didn't do that. Well, you didn't, but you called some function which was inline, which was inline, which was inline, and there is then this final call. So we need to resolve inlines too. And this is the -I parameter to Adder2Line, and now we're starting to get there. Problem is, if you would call Adder2Line for every single instruction pointer offset you get back from your tracer, it doesn't scale. It's super slow. There are some tricks like passing multiple address offsets in one go, but really what we want to do is we kind of want to re-implement Adder2Line for our specific use case. So let's do that. First off, how do we find the ELF mappings without having to parse procmap? That's actually trivial, once more, thanks to this little gem called dl_iterate_p header. It's again part of libdl. You call it, you can pass it a C pointer or a non-capturing lambda. And then within that function, you just check what is the name of this p header info struct. If it's empty, for some reason it's empty for the main executable, you just parse something back out, and then later on you can map it back to the real path to the executable. I quite frankly don't get why this value is empty, but it is. And then we just output the DLPI address, which is the base address where the shared library got linked to. Cool. So this is essentially parsing proc maps. And once again, we don't actually map during profiling. We delay this into the post-processing step, and it's quite important for performance. While recording, we just get the backtraces, and then in the post-processing step, we take the instruction pointers, translate them using this mapping, and then rinse repeat. Cool. Obviously, when we want to do this in our LD preload library, we now need to take care of DL open and DL close, because whenever you have plugin systems in your applications, they may call DL open at basically any time. And when that happens, your address space may change, or the mappings may change. So you need to update those, and this example, preload mappings.sh, does this. It also resolves the executable file using std file system canonical on proc self-exe. And now we can put it all together and get this output, for example. So this is what you do at record time. You just output the modules whenever they changed, and then you trace malloc and free and output backtraces. This is recording. And now we need to use this information to actually symbolize. And for that, we use elf-utils. Great library, I love it. Happens to be written in C. Horrible to extend for someone who doesn't like to write C, but kind of cool to use though. So, doing symbol resolution is nearly as complex as getting the backtrace, because once again, you need to look at the symbol table, you need to take compressed debug information into account, split debug info, you name it. libdwfl does all of this for us, so let's leverage that. Let's build on the top, on the shoulders of giants. Pretty trivial setup. You need to define a couple of default callbacks. So I didn't write them, I just assigned them into this callback struct. I passed that one to dwfl begin. And then when I'm done, I call dwfl end. So this is my boilerplate setup code. And then I can report elf mappings. So this is now essentially taking the output from DL iterate p header. And whenever I see a module, I call report or begin report. Then I report all the modules, and then I call end report. And this essentially updates the internal mappings within DWFL, such that then, finally, we can actually symbolize stuff. Doing that essentially means we take the instruction pointer, so this is this UN64T in this case of an named IP. We ask DWFL for the module that contains this instruction pointer, and maybe it doesn't find something, we have to deal with that. But if it does find something, we can now actually fill this symbol struct and set DSO information or symbol information and file line information. So let's go through these 3 steps. First one, DSO info means what is the name of the dynamically shared object or executable, and what is the offset of the symbol within. So this is like, the offset is this parameter that you would have passed to error to line, right? So this is already kind of interesting, but obviously not the most important stuff. More important is resolving the actual symbol name, and it's pretty trivial with DWFL2. You call this module error info, and I don't know about you, but just looking at function calls like that, I really love that we can write C++ with default arguments. You can't do that in C, so you always have to pass null pointer for optional arguments. But well, we get a symbol name back. We can use that. Cool. That's good already. Oh, and by the way, we also get the symbol offset. So this would be like the offset of this instruction to the beginning of my function entry. Maybe interesting too. And now we can rinse repeat, call some DWFL functions to get the so-called die, which is the debug information entry. And this is a dwarf struct. So dwarf is the name of the debug information format on Linux, and probably quite a few beasts too. And that one you can pass to libdwarf to get the actual file and line number and column. Cool. So we're getting close because when we get the symbol here, it's actually mangled, right? And I showed it to you earlier with the adder to line, we also have to demangle. And it's yet again pretty trivial, thankfully, because there's this ABI-specific implementation of doing demangling. So C++ filled is an executable you could use for that, but once again, it's too costly to spawn a new process for every symbol. Instead, we include this CXX ABI header, which happens to have a function with 2 underscores. Ooh, you're not supposed to use that, right? Well, better than writing my own demangler. I hope the first example where I showed this full page of a single symbol explains why I'm using a reserved function here. And this works nicely, and now I finally can put it all together to get a symbolized backtrace already. So here on the top, you see me running the preload step, and then I pass it directly into my symbolizer. So this is like these 2 steps, right? Recording and then reporting. Good. But it's missing inline frames. And to exemplify this here, at the bottom, we have the function main within the executable test client vector. So this is good, but apparently function main lives within user include blah, 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 vector.tcc line 121. No, that's not the case. And this is the effect of the inliner, right? I called the function from std_vector, which got inlined into main, and it makes it very hard and complex to understand what's going on here if you ignore inline frames. So let's do that. I hope you're still with me. This happens to be the worst part of it all, I believe, because now we're in this realm of dwarves and elves, and I happen to I really like to read fantasy, but I don't like to read the code that I'm about to write. Well, we have to start with finding the so-called compilation unit debug information entry, CUDI, or CUDI, or whatever it's pronounced in English. Okay, so far so good. I don't really know why, but that happens to be the place where I need to look. And then with this CUDI, I can call dwarf getScopes, and it essentially kind of gives me a list of inline frames, and probably more, but I'll gloss over that for now. Sorry about that. And actually, even worse, I'll just use the first scope that is being returned, because it turns out that it's not really the inline frames, but just part of it. I don't really understand it, I'm sorry. But this happens to work, and I'm essentially getting out the first scope of the CUDI for this address that I passed. And now, using this first scope die, I can call dwarf getScopes die. So here it's dwarf getScopes, here it's dwarf getScopes die. Okay, whatever. This works, cool. And these scopes actually contain the inline frames. Great, finally we're getting there. Now we need to query the file information, so embedded files that got compiled into this translation unit. And I can iterate over our scopes, find those scopes that are inlined, so representing an inline subroutine using this tag, I can distinguish between those. And this is now the interesting bits. These are the symbols that got inlined. So let's use them. Let's build a symbol resolution for that. Yet again, I can't really use a ready-made solution. I need to build some boilerplate code. The gist here is, using this kind of function, I get the symbol name, the mangled symbol name for an inline frame. So this is good. And now I can ask about more information. So essentially this inline subroutine symbol call just asks for the die name. So this was the previous slide. And then using some hacky, well, it looks hacky, but apparently that's the clean way to do that. It asks for the place where this inline function was called from. And I have to admit, when I looked at this slide over lunch today, I realized that there's a bug in the implementation now, because the symbol name that I asked for before, that doesn't belong to the source line information that I'm querying below. So there's like a, as the name says, it's the callee. I get information about the callee, not about this symbol, but the next symbol. In Hotspot and HeapTrack, this is done properly, but when I built this standalone example, I introduced this bug, so expect a fix for that on the GitHub repo soon. But the idea is the same, right? I mean, you ask these functions, you just need to fix the correlation. So you have a symbol name and then some file line column numbers. Good. And now we can actually plug it in, and this is a shortened example or output, because otherwise it would be too long. The cool thing now is that we actually see at the bottom star, libc star internals, but then main, something that we have written, and then maybe some algorithm, generate n, that uses a back insert iterator into a vector, so it calls pushback on the vector, and then that one calls emplaceback, and that one then calls mrealloc insert, and this is like internals in the allocator, default allocator for std vector. Then eventually we call operator new, and then our interceptor. Yay, we succeeded. We got a backtrace that is somewhat usable. Woo! And if you run this command on new machines, once again, the file line numbers are off. I'll fix that in a bit. Cool. Now, you go home, you try this example, you compile code with Clang, and what happens is nothing works. Oh, damn. So, problem is, Clang happens to omit this .debug aranges section. If there's any Clang developer around, I would be very interested in learning why this is, because GCC puts it in, it makes all of this work as it's supposed to be working according to the maintainer of Elf utils, whereas Clang doesn't, and everything breaks, all the tooling breaks. Damn. So option one is recompile everything and pass -g dwarf aranges, and then you get the section. Option two is what we are going to do, essentially. We will rebuild the contents of this aranges section at runtime using some more hacky dwarf library function calls that I don't have the time to go into details here. It's all part of the GitHub repo. Check it out. The whole idea here is based on this great project by Bombela called Backward CPP, which just gives you a nice way to report a backtrace whenever you get a crash or something like that. So if you're just looking for that, maybe just use this library instead. Okay, so now we can put that into our symbolizer, and I've implemented that in this symbolization _Clang folder. And when you pass that one to a Clang compiled library, it will work. Cool. So now it also works with Clang. Great. But as said, I would love to be able to do runtime attaching. And haha, when you thought what I just did was easy, or maybe let's rather say it was medium to hard, this next step, this is real black magic stuff. I'm kind of proud that I now kind of know what's going on there. I think I got the answer. Like I asked, how do you do this on Stack Overflow? And I put up this reputation bonus of 500 funny points, and someone actually took the time to respond, and well, 500 points, well deserved for him, definitely. So now let me show you how this is done. And I'm very, very appreciative of the person who helped me here. Once again, we need to do code injection, and then we need to intercept. Two things. Code injection is actually trivial. I knew how to do that already, because a debugger supports runtime attaching, and it supports calling functions. That's all, right? I mean, what do? We use the debugger and call dlopen on our function, on our library. And then the linker will put our code in place, execute any static global initializers, whatnot. So that would be enough already for most purposes. That's not too hard, right? GDB-P the PID of the application you want to attach to. But if you want to do this in a proper way, you will probably want to do a couple of tricks. So first of all, disable automatic symbol resolutions, because otherwise it's going to be very, very slow when you attach to a large application. Second is, maybe your application doesn't link against libdl. Well, happens to be the case that there's this underscore libc underscore dlopen underscore mode, which happens to work similar to dlopen, which you can use instead of dlopen, because dlopen is only available in libdl. So you can kind of say pretty much everyone will use libc, but not libdl. So this is going to work nice. And then we'll optionally call a function to pass some arguments. So first of all, we run GDB in batch mode. We disable automatic symbol resolution, and then we attach to our application. We only load the symbols from libc, because inside libc, we now want to call this function libc dlopen mode with the path to our library that we want to inject. We pass these two flags, which make it work just like dlopen would. Then we call shared library on the function that we just loaded, because that makes the symbol available, and then we can call attach init and pass some path. So for example, this would be the path where the output should be written to. You could skip that and just always write to a hard-coded path, but this is like a nice way to interact with the code and initialize it that you just injected. And then you detach and you're done. Cool. But now comes the tricky part, intercepting library calls. So, I'll try to give a rough, quick introduction to what the global offset table is and the procedure linkage table. And these are very, very fundamental things that are required to support relocations, which are required to call library functions. Because when you call malloc in your executable, you don't know the address where malloc is at, right? You only know its symbol name. And so what happens is you get a so-called relocation section within main. So here we just have this trivial example that calls malloc, again, full debug build. And if we call readelf, we can inspect the relocation table. Oh, sorry. And here we see that at a certain offset of 2000, this is actually the offset into the global offset table, that's the address where I will expect my real malloc to be placed by the dynamic linker. And when I disassemble one malloc, I see down here, it's not calling malloc directly. It jumps to the address within the GOT. So, well, put differently, it loads the address from the global offset table and then calls this. And this happens within the so-called procedure linkage table. There's some magic involved to only pay the price once, and then it kind of initializes it only once, and afterwards it's quite fast. So if you ever seen an add PLT symbol in a profiler, this is where this comes from. And down here, when you actually call malloc, you see a call to this malloc inside the procedure linkage table. So now we know what we need to do, right? We overwrite the values in the global offset table. We iterate over all relocations in our jump tables, check if the symbol name matches, because here inside the table, there's an offset into the symbol table, and within the symbol table is an offset into the string table, and this we can then use to restructure the symbol name and match that against our expectations, and then essentially put our custom hook into the global offset table, and now that one will be called. So let's try that out. Now, without preloading anything, just overwriting the GOT table. We have a function foo, it calls malloc, and we call foo, then we will overwrite the p headers, and then we will call foo again. And overwriting the p headers is, well, we once again use dl iterate p header. We will skip the linker because bad things happen when you try to overwrite stuff within the linker, so I didn't dare to do that. I then also check the sections within my P header and look for this dynamic section. So now I will iterate over all entries, all my dynamic entries within this section, and I'll override, or I'll try to override some data there. I can do that basically by, once again, iterating over all the DIN entries, and every entry corresponds to a different table. So I have a symbol table, string table, jump rel table, rel A table. For this purpose, it's enough to just concentrate on the jump rel table. This is a relocation that encodes the call to malloc later on. So we'll set up the tables, this is this loop, and then we override the GOT entries. Some type defs, gloss over it. Our table, it's not magic, it's just this table with some size, and you can call begin and end, which gives you back the entries within this table. We can use that to find the iterations or iterate over our relocations, and then get the symbol name using our string table and symbol table. This is what happens here. We get the address out, and then we try to override the GOT entry by checking whether it's malloc. And if it is malloc, we once again call our interceptor, which does what we did with LD preload before, right? Calling DLSIM, that's it. You may need to call mprotect and whatnot to actually make the address writable, but most of the time, this works. We can run it, and we see a single relocation was found, and a single call to malloc intercepted, because in our example here, let me go back. Where was it? Oh yeah, here. I first called through, that malloc wasn't intercepted, but the second one was actually intercepted. So this is pretty cool. I now somehow dynamically changed it all and intercepted the second call to malloc. This is exactly what we want, right? So now we can hook it all together, put it into one single executable, right, or shared library, and then we get something like that. So we can attach, runtime attach to a different application, and then any subsequent malloc will get notified, we can get a backtrace, we can spit it out. Pretty amazing, I believe. So, when you stop here, and this is where our time is running out, you got pretty far, but it's not yet a production-ready heap profiler. You definitely need to take your output format into account. So definitely use something like ZStandard for compressing the data, otherwise you will drown in gigabytes of data. Maybe use a binary data format. Maybe build something that is easily integrated into a time series database such that you can then later on zoom in on time slices, right? You need to handle more quirks like forking, subprocesses, threads, right? We didn't talk about threads at all. You definitely need synchronization in there too. Some kind of API for custom allocators, for pool allocators, right? And obviously some kind of UI to visualize it all. And that is HeapTrack, amongst others, a tool, open source tool that I wrote, and that will be my last example here. I'll run HeapTrack on a worst case scenario for this editor, which is like thousands and thousands of lines of repetitive C++ code. We'll wait. And the gist here is it's about 2 times slower than running the editor without any profiling. And we just traced, in this case, close to 7 million allocations. We grabbed 7 million backtraces. And what we got out is this 2 megabyte file, which doesn't sound large. And now we can visualize it. And most importantly, we get a flame graph, which I believe is the most important visualization for these kind of data. You get consumed graphs, number of allocations, you'll find temporary allocations, you name it, and right. So try it out. Don't write your own heap profiler. I would very much welcome any contributions. You can find the source code in the slides. I think I had the proper link on the first page. So yeah, that will be it. Thanks. If there are any questions? Oh. Any questions? Please go to the mic.
Last night I've been to Tooltime and saw this all in action.
I'm sorry, can you come over because the echo is so bad I don't understand anything. Could you maybe come here and I'll repeat the question then? That's probably easier, sorry.
Last night I've been to Tooltime and I've seen this all in action and it looks really amazing. Do you have any videos that show in action everything that you have written?
I think on YouTube you should find something from us. Oh, and by the way, before you leave, grab a t-shirt. That's very important. Like one of these awesome t-shirts. Free, take them before you leave. So yeah, on YouTube you can, I think, find a demo for that on HeapTrack. Yeah, definitely. So next question. Maybe you just talk and I'll repeat it.
Do you have any support for doing this on an embedded Linux system? So it's on a different
Right. So the question is whether I have support for running this on embedded Linux. Yes, the answer is yes. We do this all the time. With exclamation mark, it's not yet perfect because you actually still need the debug information or need to run some custom commands. It's doable. I need to polish it a bit, but it's doable. I've done that on ARM V8, works. Yeah, next question.
Have you seen any negative impact that no-except specifications have on your backtraces? Because if I recall correctly, for no-except functions, there are no exception handling frames emitted.
So the question is whether I've seen negative impact on the quality of the backtraces in face of no-except. I have not. Last time I talked to an Intel developer on the Linux perf mailing list, he said that on x86, at least by default, every code is kind of compiled with -f asynchronous unwind tables anyways. So unless you change the default, you will get unwind entries. Even for no-except functions. I think. Try it out, I would guess. Next question.
The library used for doing the symbol resolution, does it automatically detect like debug symbols if you have strict binaries, or you have to go do that?
Okay, so the question is whether AlfUtils is going to find debug information automatically for me when it got stripped from the original. So kind of related to the question for embedded systems, right? Let me go back to the setup. Here. So by default, it will call this standard find debug info, which essentially looks into some heuristic paths and tries to find debug info there. If it doesn't find that, it will try to look up stuff via build ID. If it doesn't work, you're lost. But the very last path here, this null pointer, is the user supplied string to further lookup paths. So this would be a customization point for that purpose.
For Doug, I have a question. In GUI, you have a path with temporary allocation. What is temporary allocation?
Okay, so the question is in HeapTrack, what does a temporary allocation mean? It's a very trivial heuristic that I played around with once, and it happened to be super worthwhile. So this is at analysis time, right? I don't see what happens in your code. I just see there's an allocation followed directly by its deallocation. So there could be seconds in between, I don't care. But as long as the allocation is followed by its deallocation, I call it temporary. And just this trivial heuristic will find tons and tons of interesting inner loops where you allocate memory accidentally, and you can just hoist out the allocation out of the loop, and it's like a free performance win, basically.
Okay, thanks.
Yeah, you're welcome. Hi.
That was quite the black magic. Do you have any plans, or do you already have it done to pull this out into a usable, easy-to-use library?
So the question is whether it's doable to put this into a reusable library. I would guess the GitHub repo that I wrote for this purpose is kind of like the starting point. So help welcome there, because my tools have it all integrated yet, right? So you could just essentially build on top of that. But no, I haven't yet written a library, because once you would do that, you would probably want to support more platforms, right? But it would be a great project, definitely. Help welcome. Cool. So again, grab a t-shirt. Yes, we are out of t-shirts. That was my most important tool. So thank you, everyone.